Okay, I'm going to spend a bit more time talking about orders of integers. And last time we demonstrated that finding the order of an integer modulo, well, we tried a couple of prime numbers, I think it was 7 and was it 13? It can be quite tricky, so we need all the help we can get. Well, anyway, let's have a look at it. So let's just say that A has order k. This is all modulo n. Then a to the power h equals 1 if and only if k divides h. K divides h. Well, one of the directions is trivial and the other one's only a little bit harder. So let's have a think about this. Then a to the power h equals 1 if and only if k divides h. Let's assume that k divides h. What does that tell us? That tells us that h. Oops! Oh dear. That tells us that h equals, let's say, alpha k for some alpha. Okay. So a to the power h equals a to the power alpha k equals a to the power k to the power alpha equals 1 to the power alpha equals 1. Okay. So that's one direction. And now we'll do the other implication. So you see, if k divides h, then a to the power h equals 1, which is kind of obvious, really. Now let's have it looked at the other way around. If a to the h equals 1, we want to show that k divides h. Okay, so how do we do that? Well, if a to the power h equals 1, then k is by definition less than or equal to h, because k is the smallest power that we'll do. So we can write h equals alpha k plus r, and further we can arrange that r is in the range 0 to k. Okay, just by considering h modulo k. So what does that tell us? Let's have a look at a to the power h now. Well, that's a to the power alpha k plus r equals a to the power k to the power alpha times a to the power r equals a to the power r. Oops. Which equals 1. So we know now, so therefore r equals 0. R must be equal to 0 because we know that r is less than or equal to k. No, in fact it's strictly less than k. R is strictly less than k, of course. If you're doing everything modulo k, you can't have a k there, or you don't want a k there. So r is strictly less than k, but we also know that k is greater than or equal to r as well. No, we don't. R is less than k. That tells us that r equals 0, because if r was greater than 0, the order would be r, not k, and it isn't. So r must be equal to 0. So that tells us that k divides h. Let me write that whole thing out again. Integer a has order k. Then a to the power h equals 1 if and only if k divides h. And so specifically, we know that a to the power phi of n equals 1. So h equals phi of n. So k, which is the order, satisfies k divides phi of n. Okay, because I'm using k divides h. So that's quite a nice little theorem, that. So let's try using that. Let's work out what the order of 2 is. What is the order? What is the order of 2 is? What is the order of 2 modulo 13? Well, we know that 2 to the power 12 equals 1 modulo 13. And by this theorem here, we know that k equals the order of 2. We know that k divides 12. Okay, so we know... having difficulty controlling this. K divides 12. So k must be equal, well, it can't be equal to 1, 2 or 3 or 4 or 6 or 12 itself. So this cuts it down quite a lot. Before, when we were doing this, we were trying to figure out the order of something. We had to raise our 2 to all these different powers. But we don't need to we don't need to do so many now. We only need to try these guys. And we established before that all these guys were not equal to 1. So the order was equal to 12. Because 2 to the power anything in the set 2 or 3 or 4 or 6 was not equal to 1. So the order was equal to 12, which is quite nice. And I'm going to stop there.